Hello and welcome to this module 8. In this module, we will be seeing about uh, the first optimization technique of FSMs, which is called state reduction. So the goal of this lecture is to reduce the number of states in your finite state machine. So the students are expected to reduce a given state diagram or the next state table into the reduced number of states. So as we know, the number of flip-flops is determined by the number of states. So here you can see we have the formula where the number of flip-flops used would be the ceiling of log number of states to the base 2. So therefore the number of states determines the number of flip-flops, and for a particular given circuit or for a particular problem, when we derive the state transition graph, we usually have more number of states, and in some cases we have unused states, or it might be redundant, or in certain cases it might be actually simply equivalent. So you can actually simply merge two states together because they are equivalent. And as far as the total number of states is less than 2m, which is for we have about m flip-flops, then we can basically get an optimized FSM or optimized FSM circuit. So here is a simple example. So you have your next state table and your state transition graph. So if you are looking at this particular example, and then we can see there are some instances in which there will be two states that are identical or they're equivalent. So therefore you can basically, let's say for example, remove the state that is H, and we can see that this particular state is very similar to this state because it has the same kind of next state as this, and the outputs are also the same. So therefore they are what we call as equivalent. So we can say D state D is equivalent to H, and now wherever H is being used, so we can actually simply replace that by D and then get rid of this state. Technically you are merging these two states into one single state, and so on and so forth. So in this case what is happening is, as you can see, we see that these two states are going to be identical. So what defines equivalency? That means two states are equivalent. So two states are equivalent if both states produces the same output. So that's the first condition you need to check. So if the outputs are different, then the states are not equivalent. So they actually produce, if it's a Mealy's, then they should actually produce the same output for every input. So so in the case of a Morse, it's basically would be only not dependent on the input, so they will have the same output. And then both states should have the same next state for every input. So that's what this is, which is D and H. So here you can see that when x is equal to 0, it goes to G. Here again H, when x is equal to 0 goes to G. Similarly, when x is equal to 1, D goes to A. Similarly, H goes to A when x is equal to 1. And first and foremost, their outputs for the respective inputs are the same. So therefore we can say that D is equivalent to H. So then what we do is we basically replace H by D, and now you can see there is also other states, like for example, once that is equivalent, you can see that we have other states like so we can see that we have state which is B, which has DC for 0 0, and E also has DC for 0 0. So therefore we also have another condition where we have B is equivalent to E, state B is equal to E, and so we can actually strike the state off, and wherever we have E, we can actually basically replace that by B. And so once we do that, then now we look at it and we see that now the states C and F are also C and F. Now they are not equivalent because their outputs are different, so they are not equivalent. And then we can see once you actually eliminate that, then we see that now A and C are equivalent because you have FB, and they have their output 0 0 0 0. So therefore C also can be taken off, and wherever we have C, then we can basically also replace that by A's. So that's basically how you can do equivalency checking. And then here initially we had 1 2 3 4 5 6 7 8 states, and now we have removed 5 states, so sorry, 3 states, and now our solution will be basically made up of lesser number of flip-flops. So here is our reduced table. So here, as you can see, this was our original 8 states, and we have 5 states. So for the 8 states, the number of flip-flops would be basically ceiling of log 2 to the power 8 states would be 8, and that would actually mean that you have say 8 is 3 flip-flops, and even if you have for 5 states, it's log 2 to the base 5, ceiling of that will still give you 3. But if you actually implement this circuit, you can see that we will have more don't cares, because let's say if you have a code 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0, the rest of them is basically going to be don't cares. So you're going to have a lot of don't cares in your implementation, and this one is actually going to give you a fewer number of gates. So here is another example. The type of problems the student can expect is that you would be actually given an unreduced say state transition graph or next state table, and you're supposed to do a state reduction and then implement the circuit and determine what is the resultant area or resultant transistor count. All right, so here, as you can see, we have quite a few. So we take H, which has A as your next state values for x is equal to 0 and x is equal to 1, and output is again 0 0 for x 0 and 1. And then we see that for I we have the same thing, for the K we have the same thing, M we have the same thing, N we have the same thing, and P we have the same thing. So basically we have all these states that are identical, so we can eliminate these states and just keep H alone. And then we also see that for this condition, when you have J, which is AA01, and then which is L, which is AA01. So therefore those two states are identical, so we can eliminate L. And what we do is, since we are going to eliminate I, K, M, N, and P, all these are going to be changed to the equivalent state of H. And in the case of L, we are going to replace it by J. So we have one iteration. So once that iteration is done, so now you can see that D and G have H, and 0, 0, 0, 0. Therefore, in the second iteration, we see these two are equivalent. And then we also see that E and F is JJ, HH, 0, 0, 0, 0. So they are both identical. So therefore, we keep D, eliminate G, we keep E, eliminate F, and then also replace all the F's by E, all the G's by D. And so you end up with 1, 2, 3, 4, and 5, only 5 states. So we initially started with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We started with 15 states, and now we are only having 5. So the number of flip-flops in the unreduced would be log 2 to the power 15, which would be 4 flip-flops. And now we only get log 2 to the base log 5 to the base 2, which will be only 3. So you actually get a reduction in entire flip-flop and then all the circuits associated with it. So you're going to have a huge reduction in area in terms of gates and transistor counts. So here is another example. So here you can see that we are looking at equivalence, and we see that we have A and A, and then again A and A, but they have two different outputs, so they are not equivalent. And then we are going through the rest of it, and we see there is no equivalence. So the equivalence itself, there are two types. One is where you have explicit, as we have seen in the previous cases, where let's say you have two states X and Y, but when let's say you have an input, say W is equal to 0, W is equal to 1, and it goes to a state Z, 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 and Z, and then the outputs are also the same, let's say 0, 1, 0, 0, 0, 0. So we say explicitly they are equivalent. But in some cases, they are also having a type of equivalence that is called implicit equivalence. So which means there is no direct conflict. So if there exists no different, no explicit conflict, and then they can be treated as equivalent. So it's basically like, it becomes like a don't care. So how do we go about doing it? So we actually create what we call as an implication table. So in the implication table, so here we can see that we have these states, which is A to H. So what we do is we write our, let's say on our x-axis, we start from A down to G, and then on your kind of a horizontal axis, we start from H and then go all the way to B. So pretty much, so that's the kind of sequence that you will need to take. So let's say, so that's what we did here. So you have A, B, C, D, E, F, G till here, and then you go to H, G, F, E, D, C and B and not A. So here basically we are trying to plot an implication, which is whether they are in conflict or they are not in conflict, and what conditions they are in conflict and what conditions they are not in conflict, and so on. So here you can see that this is a relationship between A and B. So what is the relationship between A and B? Is it says that if you just take A, it has A is CD and the output is 0, so it's a motion machine. And then B is F and H and it also has 0. Now, since the outputs are the same, there is a possibility that they could be equivalent, provided if D is equivalent to F and C is equivalent to H. So if these two conditions are met, then we could probably say that A and B are equivalent, because these conditions are actually implying that A and B can be equivalent. So that's why it's called an implication chart. So instead of actually representing them as the equivalent sign, we also can just simply put it as a dash, which is to indicate a pair of equivalency, that is D should be equivalent to F and C should be equivalent to H. So anyhow, so therefore we create an implication chart for every row with every other row in your next state table. So here we can see the reason why automatically A and C, they can never be equivalent, because one has an output which is 0 and the other one has an output which is 1. So those can definitely not be equivalent, no matter what the next state implies. So therefore you can see that we can always mark some conditions which are in excess, that basically denotes that these can never be equivalent. So here we saw this condition. So now here we see about A and D. So for A and D, you can see that this is D and A should be equivalent. That doesn't give us much information because we are looking at A and D, and then this one says C and E. So therefore you don't have to write the other condition, just basically C should be equivalent to E. Similarly, when we are looking at A and G, so D has to be equivalent to B, C has to be equivalent to H, and the output is 0, so that condition is listed, and so on. So in the implication, we actually go through multiple iterations. So this is your initial implication chart. So now what we do is we can see that we see D and F. We go through D and F. You can see D and F is marked with not equivalent. So there is no way that A and B is going to be equivalent. So therefore you can also list the new condition, which is A and B are not going to be equivalent. So now we are looking at C and E. So if you look at C and E, so it says that it's dependent on one condition, which is A and D. So, and then which is A and D, you're not able to make addition, so we will leave as is. So now we are going to look at this A and G. It's looking at BD. So we have BD. For now, you can see it has no information. We're just going by this. So it has no information here. C and H, C and H, you have some conditions, so we will keep it as it is. Now we go to this, which is B and D. So we look at B and D. So we already saw that it's dependent on A and F. So this is A and F is already gone. So now we do that. So now we also have another condition, B not equal to D. Cannot be equivalent to this. And now we look at this condition, which is going to be BF. So BF is already marked there. So we're going to do this. So now we also have another condition, which is B and F. Now go to C and E. and you can see C and E is dependent on A and D, which is unresolved there. Now this condition E and F and B and D. So here we know that by this condition E and F, but B and D, we have this condition, they're not going to be there. So we are going to mark it as they cannot be equivalent. So C and H, again C and H based on C and E. C and E is undecided, and DG, we have not decided on the DG yet. Okay, so then comes this condition, which is DG. We have AB, so which is already not going to work, so we are going to strike it off. And then we have, this is E and F. E and F is C and F, and A and B, which is also not there. We're going to strike it off. This C and H is A dash G, which is again unresolved. Leave it. Go to F and H is C and F, and C and F. And okay, so I forgot to update the thing. So here we have D and G, and then apart from that we have E and G. So here you can see that we also have BD and BG. Okay, B and G. So here we can see that we have that condition B and G, so therefore that will basically form our first iteration. So it's called the first pass. And then we go to the second pass, which is, again, we're going to consider all these conditions, and we're going to do it because since we actually started to be in this, we were going in this fashion, you can see that you'll have more conditions that are occurring here, and you're not going back and updating it here. So we are now going to do the updation here. So now here you can see that's already gone. So the conditions that are left over is going to be this. So but we have B and D not there, so it's going to get struck off. This condition C and E, D and G is there, that condition gets struck off. This was still AG was pending. Here we have an updated here, which is AG. Therefore, so let me put this AG, new conditions AG, new conditions C and H. So that goes off, and so the only thing that is now left is this two conditions. So basically what it's saying is A can be equivalent to D if C is equivalent to E. And so that's what this is saying. And this one here is saying C and can be equivalent to E if A is equivalent to D. So basically one is saying I have no problem if C and E are going to be equivalent, I have no problem being equivalent, and the other one is saying if A and D are equivalent, C and E, I don't have any problem. So basically they are implicitly telling us that these two conditions, which is A and D, can be equivalent, and C and E can be equivalent. So basically these are the two implicit equivalencies that are there that we come, and therefore we can eliminate those from our initial thing. So which here going back, so here you can see that's a state where we have eliminated E, and we've also eliminated D. So A was equivalent to D and C was equivalent to E. So C and A are retained and D and E are eliminated. So what you have here as 8 states now becomes 6 states in our reduced table. So here is an example that is shown, and as you can see, this is a BCD to XS3 converter. So you have your bunch of inputs, and that's your outputs. So that is basically what actually happens is these are your current states, and this will be your outputs. So and then what we do is, as you can see, that we have an input sequence that is coming in. So depending on what input sequence that is coming in, we basically will need to, if you have this particular input, so first we have 0 0 0 0, then the output that should be generated should be 1 1 0 0. So and then technically this forms, as you can see, that would be your state, your next state table, and then this is your state transition graph. And we can then apply reduction, and you can see that we only get a fewer number of states, and this will be your final reduced state transition graph, and this is your reduced next state table. So I would leave you guys to actually work this problem out by yourself, and I will also try to post the individual solutions later. And here is, as you can see, we then assign codes for every state, and this you have an unused state, so you actually have don't cares. And now we are using a D flip-flop, so simply change it to D1, D2, and D3. Get equations for D1, D2, and D3, and you also have an output which is Z, and so this becomes your standard FSM controller design. So we have our the D1, D2, and D3 equations, and this will be your output equations that are generated. So as I said, I would allow you guys to actually work this out, and if you have any questions, let me know. And then I also have two other problems which will be for your practice, and I will post these solutions also online. So in this module, we have seen that how to perform a state reduction in sequential system, and the advantages of performing state reduction is to reduce the number of flip-flops, as well as to reduce the number of gates, as reduction in states will lead to introduction of more don't cares, and thereby reduction in area. Thank you.